Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 7, Coordinate Systems in 2- and 3-Dimensional Forms. Section 67, Linear Transformations in a Plane. We inquire now concerning the geometric properties of a linear transformation. Equations 1. Rho x1 prime equal to a11 x1 plus a12 x2 plus a13 x3. Rho x2 prime is equal to a21 x1 a22 x2 plus a23 x3. Rho x3 prime equal to a31 x1 plus a32 x2 plus a33 x3. Such a transformation transforms any point x1, x2, x3 of the plane into a unique point x1 prime, x2 prime, x3 prime of the plane. Reciprocally, to every point x prime will correspond a unique point x, provided the determinant of the transformation, a equal the determinant by column a11, a21, a31, a12, a22, a32. a13, a23, a33 is not 0. For we may then solve equations 1 for the ratios x1 to x2 to x3 in terms of x1 prime to x2 prime to x3 prime as follows. Equations 2, rho prime x1 equal to a11 x1 prime plus a21 x2 prime plus a31 x3 prime. Rho prime x2 plus a12 x1 prime plus a22 x2 prime plus a32 x3 prime. Rho prime x3 equal to a13 x1 prime plus a23 x2 prime plus a33 x3 prime. Here, the coefficients a sub ij are the cofactors of the elements a sub ij respectively in the determinant a. Further, equations 1 transform every line in the plane into a unique line. In fact, the points x satisfying the equation u1 x1 plus u2 x2 plus u3 x3 equal to 0 are, by reference to equations 2, transformed into points x prime satisfying the equation. The quantity a11 u1 plus a12 u2 plus a13 u3 close paren times x1 prime plus the quantity a21 u1 plus a22 u2 plus a23 u3 close times x2 prime plus the quantity a31 u1 plus a32 u2 plus a33 u3 close times x3 prime equal to 0, which is the equation of a line. If the coordinates of this new line can be denoted by u1 prime, u2 prime, u3 prime, we clearly have the following relations between the coordinates u1, u2, u3 of any line and the coordinates u1 prime, u2 prime, u3 prime of the line into which it is transformed by equation 1. Equations 3. Sigma u1 prime equal to a11 u1 plus a12 u2 plus a13 u3. Sigma u2 prime equal to a21 u1 plus a22 u2 plus a23 u3. Sigma u3 prime equal to a31 u1 plus a32 u2 plus a33 u3. We have seen thus far that 1 represents a collineation in the plane in point coordinates. The equation 3 represents the same collineation in line coordinates. It is readily seen, finally, that this collineation is projective. For this purpose, it is only necessary to show that it transforms any pencil of lines into a projective pencil of lines. But it is clear that if m equals 0 and n equals 0 are the equations of any two lines, and if 1 transforms them respectively into the lines whose equations are m prime equals 0 and n prime equals 0, any line m plus lambda n equals 0 is transformed into m prime plus lambda n prime equals 0, and the correspondence thus established between the lines of the pencils has been shown to be projective. Theorem 6. Having shown that every transformation, 1, represents a projective collineation, we will now show conversely that every projective collineation in a plane may be represented by equations of the form 1. To this end, we recall that every such collineation is completely determined as soon as the homologous elements of any complete quadrangle are assigned. Theorem 18 of Chapter 4. if we can show that likewise there is one and only one transformation of the form 1, changing a given quadrangle into a given quadrangle, it will follow that, since the linear transformation is a projective collineation, that it is the given projective collineation. Given any projective collineation in a plane, let the fundamental points 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 1 of the plane, which form a quadrangle, be transformed respectively into the points A equal A1, A2, A3, B equal to B1, B2, B3, C equal to C1, C2, C3, and D equal to D1, D2, D3, forming a quadrangle. Suppose now we seek to determine the coefficients of a transformation 1 so as to effect the correspondences just indicated. Clearly, if 0, 0, 1 is to be transformed into A1, A2, A3, we must have A13 equal to lambda A1, A23 equal to lambda A2, A33 equal to lambda 3, lambda being an arbitrary factor of proportionality, the value not equal to 0 of which we may choose at pleasure. Similarly, we obtain A12 equal mu B1, A22 equal mu B2, A23 equal mu B3, A11 equal nu C1, A21 equal nu C2, A31 equal nu C3. Since, by hypothesis, the 3 points A, B, C are not collinear, it follows from these equations and the condition of Theorem 4, Corollary 2, that the determinant A of a transformation determined in this way is not 0. Substituting the values thus obtained in 1, it is seen that if the point 1, 1, 1 is to be transformed into D1, D2, D3, the following relations must hold. Rho D1 is equal to C1 nu B1 mu A1 lambda. Rho D2 is equal to C2 nu B2 mu A2 lambda. Rho D3 is equal to C3 nu plus B3 mu plus A3 lambda. Placing rho equal to 1 and solving this system of equations for nu, mu, lambda, we obtain the coefficients A sub ij of the transformation. This solution is unique since the determinant of the system is not 0. Furthermore, none of the values lambda, mu, nu will be 0. For the supposition that nu equals 0, for example, would apply the vanishing of the determinant. The determinant by column D1, D2, D3, B1, B2, B3, A1, A2, A3, which in turn would imply that the 3 points D, B, A are collinear, contrary to the hypothesis that the 4 points A, B, C, D form a complete quadrangle. Collecting the results in this section, we have Theorem 8. Any projective collineation in the plane may be represented in point coordinates by equations of the form 1 or in line coordinates of the equation of form 3, and in each case the determinant of the transformation is different from 0. Conversely, any transformation of one of these forms in which the determinant is different from 0 represents a projective collineation in the plane. Corollary 1. In non-homogeneous point coordinates, the equation of a projective collineation are x1 equal to the quantity a11x plus a12y plus a13 divided by the quantity a31x plus a32y plus a33. Y prime is equal to the quantity a21x plus a22y plus a23 divided by the quantity a31x plus a32y plus a33, provided the determinant by column a11, a21, a31, a12, a22, a32, a13, a23, a33 is not equal to 0. Corollary 2. If the singular line of the system of non-homogeneous point coordinates is transformed into itself, these equations can be written x prime equal to a1x plus b1y plus c1, y prime equal to a2x plus b2y plus c2, provided the determinant a1, a2, b1, b2 is not equal to 0.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.